Hello everyone. Let's start with a curious question. Why do objects in water feel lighter than on land? Why do swimmers float more easily in deeper pools, or why do submarines rise and sink in oceans? The answer lies in the concept of upthrust. Liquids exert pressure at every point, not just downward, but equally upward, sideways, and in all directions. What's more, this pressure increases with depth. That means the deeper you go, the stronger the pressure becomes. So, when an object is immersed in a liquid, the difference in pressure at different depths becomes the very reason behind the buoyant force or upthrust. Imagine immersing a solid block of cross-sectional area A in water, as shown in the diagram. The bottom face of the block lies deeper than the top face. Now, the pressure on the lower face, let's call it P2, is equal to H2 times rho times G. The pressure on the upper face, P1, is equal to H1 times rho times G. Since H2 is greater than H1, P2 is always larger than P1. This simple inequality between P2 and P1 is what causes a net upward push on the block. Nature is quietly balancing forces through fluid pressure. Let's now calculate the actual buoyant force. The force on the bottom face is F2, which equals P2 times A. The force on the top face is F1, which equals P1 times A. So, the net upward force, or upthrust, becomes F subscript B equals open bracket P2 minus P1 close bracket into A. This is the buoyant force acting on the body. A simple difference in pressures multiplied by area gives us this upward push we call upthrust. Now you might wonder, what about the side walls of the block? Don't they also experience pressure? Yes, they do. Liquids exert pressure on all sides. But here's the catch. The pressures on opposite vertical sides are equal in magnitude and opposite in direction. They cancel each other out perfectly. So, the only unbalanced forces are the vertical ones, greater pressure at the bottom minus smaller pressure at the top. That's why the resultant force is only upward, giving us buoyancy. Let's take a special case to see this more clearly. Suppose we immerse a thin sheet, like a lamina, in water. Since its thickness is negligible, the top and bottom surfaces are at almost the same depth. That means P2 and P1 are nearly equal. The difference between them becomes so tiny that the upthrust vanishes. What happens then? The sheet sinks under its own weight, as if no buoyancy existed. This tells us that thickness, or the vertical height of a body inside the liquid, is essential for buoyant force to act significantly. Alright, let's derive the general expression for upthrust step by step. Take a block of height 8 and cross-sectional area A, completely immersed in a liquid of density ρ. Step 1. Pressure at the top face, P1, equals H1 times rho times G. Pressure at the bottom face, P2, equals open bracket H1 plus H close bracket times rho times G. Step 2. Net upthrust equals open bracket P2 minus P1 close bracket into A. Substitute the values. F subscript B equals open bracket rho G H close bracket into A. Step 3. Since area A into height H equals the volume V of the block, we can write F subscript B equals rho times G times V. That's our golden formula. The upthrust is equal to the weight of the displaced liquid. So let's wrap this up. Liquids exert pressure in all directions, but this pressure increases with depth. Because the bottom of an immersed body is at a greater depth than the top, there is a net upward force, the buoyant force or upthrust. Mathematically, F subscript B equals open bracket P2 minus P1 close bracket into A, which simplifies beautifully to rho times G times V. The horizontal forces cancel out, leaving only this vertical difference. That's the real reason why boats float, why balloons rise, and why you feel lighter in water. I hope this session gave you a clear picture of the reason for upthrust. In our next lesson, we'll connect this to Archimedes' principle, a law that revolutionized physics centuries ago. Until then, keep observing the world and ask yourself, is this floating, sinking, or balancing? Because behind it all lies buoyancy.